acid-base review from AP Central, they weren't able to get to the last question. So here it is. Write a net ion equation for the reaction. You're supposed to remember that alkali metals, the alkali metal like sodium will be a spectator ion, and then strong acids, the anion will be a spectator ion. So know all the strong acids. We do a titration. So titration is where moles of the acid and moles of the base are equal based on the stoichiometry of the reaction. In this reaction, the stoichiometry is 1, 2, 1. And so this calculation will give me moles of the acetate. Now, one of the things I did is I just used milliliters, because in the next equation, I'm also going to use milliliters. But you should consider always using liters. Instead of saying 20 millimoles, I would have said 20 moles, and that would have been wrong. So just be careful. Using the liters is always the correct answer. And sometimes if you have 2 milliliters that you're going to be using, you can do that. 3 significant figures because of the 1.20 is 3 significant figures. All right. That was A. When an indicator has a pKa similar to that of the acid, the indicator changes at the equivalence point. The pKa of our acid is 4.8, so we're going to look for something close to 4.8, and I'm going to say it's methyl red. All right, I'm going to go through all this. It's all true, but not for this equation, but there's a point to that. So everything I say is essentially correct, but we're going to fix it at the end of the slideshow. So pH and pKa are equal at the equivalence point, and if we take our Ka, 1.6 times 10 to the negative 5, we get 4.8, and so the pH at the half equivalence point is 4.8. And then we have to plot it, and so I'm going to plot 4.8 as the half equivalence point. So I measured this as like 16.6. So you may have it shifted a little bit. I know that the acid will be at the very bottom, and I know that I'll have a flat line, the buffering effect at the half equivalence point. I'll have a straight line for the equivalence point, and I know at the end it'll be flat too. So I'm going to connect all these lines, not just the points, I'm going to connect the lines so that I have a nice curve. And there you go. And that would be the sketch. It did say to mark the half equivalence point, so we'll put an X in there. We move on to part F. I don't remember what E was, but we move on to part F. And the dilution equation is just a way of saying that the moles in a dilute solution and the moles in a concentrated solution are the same. This is my dilute solution, this is my concentrated solution. If I multiply these together, I get moles, and so those are the same. So then, again, I'm using milliliters in this equation, so my answer will be milliliters in the equation. And I did an extra, oops, sorry, I wanted to type. It actually says 2 significant figures, not 4, so rats. All right, determine the pH of this benzoate solution. So I get the Ka, and I work it out. And I realized that this actually is asking for, if we set this up in, I don't know how to get Presentifier. We set this up for acids, so I need an acid solution. And I don't have an acid solution. I have a base solution, so I can't really use Ka. What I need to use is Kb. So I find Kb, which is, this is the Kw, 10 to the negative 14. I find it. And now, see, I can use a benzoate solution of 0.069, and I can solve for X, and X, of course, is OH. Well, then we're going to take the POH, and then we're going to subtract that from 14, and we're going to get the pH. And so here's the pH of my basic solution, and that pH is good for a basic solution. So perfect, I did that. And then we have to determine the mass of this benzoate solution. So I multiply to get the moles. To be perfectly correct, benzoate and sodium benzoate are different substances, but they are 1-to-1. And then I multiply by the 144. That was given to you at the very, very, very beginning of the lecture of the problem. So it's way up here. And I often hate problems where part of the solution is buried deep inside of the question, and so you have to go back and find it. And so this is just one of those choices. All right, so let's go back so you can stop. Sorry. All right, so there you go. Also 3 significant figures. Nope, that's just 2. So again, this should have been 2.0. So already I've messed up on the number of significant figures. Because I think that would be a problem where they would check significant figures. All right. In light of our new information, so back here, our new information is that the benzoate solution is not calculated well if you use Kas. You have to use Kb to find out information about the base solution. So on my graph at the beginning, it's all about the base solution. So what I need to do is I need to work with Kb to figure this out. Now it turns out Henderson-Hasselbalch can be used also for Kb and POH. So if this is Kb, you can plug a negative log value into all that, and if these two are equal, which they are at the half equivalence point, then the last term goes to 0, and pKb equals POH. And that means that our POH at the equivalence point is 8.20. I'm sorry, our POH is 8.20 and our pH is 6.8. All right, so we got to go back up and change that. So let's cross out our original value and put 6.8. And then, since pKb was used instead of pH, we might want to look at our indicators here. And pKa and pKb add up to 14, just like pH and POH. And so actually 9 is good for this 8.20. So I'm going to stick with methyl red, although I may change the answer there a little bit. The graph, though, does have to be changed. It looks a little weird, and if you drew it and go, that's strange, I did too. I drew it, and then I realized after I got to this problem I needed to go back. So I just wanted to show you how easy this would be. We're going to move our equivalence point up, but everything else is essentially the same. We're going to follow the line similarly. It just doesn't have to go down quite so far. And this actually looks a lot closer to weak acid, weak base titrations that we've seen before. So we got to change that graph. All right, that's the end of our little explanation.